In today's lesson, we're going to be looking at Chapter 4, Lesson 5 on solving fraction equations. What we're going to see is this is going to be very similar to when we looked at decimal equations, and our goal then is going to be to use inverse operations to isolate the variable. As I just mentioned, this is going to look a lot like when we worked with decimal equations, so there's a couple big ideas we talked about then that I want to review before we get started today. So we're going to need to use inverse operations to help us solve. Important for us to remember that the word inverse is just like the word opposite, so you should think about that there. So we want to look at operations that are opposite of each other. So when we look at addition, our inverse is going to be subtraction. When we look at subtraction, our inverse is going to be addition. I'm just going to abbreviate here for room and space. Multiplication, our opposite is going to be division, or to divide. And with division, our inverse is going to be multiplication. So if we can remember those four simple relationships, we should be able to easily solve fraction equations. We want to remember to think of algebraic equations like a balance. That means that whatever we do to one side of an equation, we must do to the other side, and we're going to have to show that work, just like we did when we worked with decimals. So again, we must show what we do to both sides of an equation. It's imperative because we can't change an equation, we can't take something away without doing it from both sides. Otherwise, we're changing the equation. By doing it to both sides, that's what allows us to use that strategy to help us solve. And then the idea of isolating the variable is going to be really important to us. We've talked about that before. That just means to isolate something means to make it go by itself, to keep it away from everything else. So we're just going to make changes to our equation so that we can get that variable all by itself. There's a couple important steps we're going to need to follow in order to solve fraction equations. The first one is important. For addition and subtraction equations only, we must rewrite the equation by substituting equivalent fractions so that all fractions have a common denominator. Again, this just goes back to what we know about adding and subtracting fractions. With adding and subtracting fractions, we know we need equivalent fractions. With multiplication and division, we do not need those, so that's why we only have to do this in an addition or subtraction equation. Well, when I look at this equation, the only operation I see here is subtraction. So my first step is going to be to rewrite this, and I'm going to have to figure out what denominator I should have. Well, when I look at 6 and 15, I know that 30 is going to be a common denominator because both of those numbers go into 30. So I'm going to start off by putting my common denominator down. Now if I look at 5 times 5/6, I had to multiply 6 times 5 in order to get 30 as my denominator. So to get an equivalent fraction, I'm going to do the same thing to the top, and that's why I come up with 25. 15, I only had to multiply by 2 in order to bring it up to 30, so I'm going to do that same thing over here. So I'm going to have a new equation that says x minus 25 over 30 equals 2 over 30. Then it says use the inverse operations on both sides of the equal sign to isolate the variable. So right now the variable is not by itself. It has this minus 25 30s attached to it. So I'm going to have to use my inverse operation. Since I have subtraction, I'm going to do addition then. I'm going to add 25 over 30 to this side. What those do is they cancel each other out. I'm also going to have to add my 25 30ths over here. So on the left side of my equation, then I've gotten rid of all this, so all I have left is my x variable, which is good. That's what I wanted. I wanted to isolate it. On my right side, I now have to figure out what 2 over 30 plus 25 over 30 is, and when I add those, I get 27 over 30. Now when I'm looking at those numbers, 27 over 30, the last thing I have to do is decide whether or not I have to simplify. Well, I know that 3 goes into both of those values, so 3 is going to go into 27 9 times, and 3 is going to go into 30 10 times, so my final answer is going to be x equals 9/10. Now, the nice thing about fraction equations like this is I can always check my answer. What that involves is taking my answer, 9/10, and putting it in place of the original problem that I have. So instead of the x there, I'm going to put 9/10, and I'm going to take away 5/6 from it. Now 9/10 I know I can rewrite as 27 over 30. I'm simply getting that from the fact that we already did that work. I don't have to do the work over again. I know that these two expressions are equivalent. 5/6 I already rewrote over 32. I know that it's 25 over 30, so I can take those away. And I'm left with 2 over 30, and 2 over 30 can be reduced to 1 over 15. Since my 1 over 15, when I checked, matched what I had in my original problem, I know that this equation is correct and that x must equal 9/10. For our next problem, we have, this time, an addition equation. So I'm going to start the same way by finding a common denominator, and I'm going to do 16 this time. That way I only have to change this equation. Since I multiplied 4 times 4 to get 16, I'm going to multiply 1 times 4 and get 4. And that equals 7/16. Now I need to use the inverse operation. So since I have addition, I'm going to take away 4/16. I'm going to do the same thing over here. These will cancel. That leaves me that g equals, well, I have 7 over 16 minus 4 over 16. So if I subtract those numerators, I'm just going to get 3. And that will be my final answer. Again, I love with algebra that I can go back and check this work. If I did 4/16, I apologize, I was looking up at the 4/16 here and not at my original problem. When I go to check, what I want to do is take a look at the original problem, and instead of g here, I'm going to replace it with my answer. So I'm going to write 3/16 there. So if I have 3/16, from my original problem, I'm going to add 1/4, except instead of adding 1/4, I'm going to add 4/16, because I know that 1/4 and 4/16 are equivalent. And if I add those, I will get 7/16. Since my 7/16 here matches 7/16 in my answer, I know that I got my answer correct. Looking at my next example, what I immediately notice is I don't see an operation symbol. When I have my x, it's not isolated yet, it's not by itself, it's attached right to a 3/4. But I know that when I see a number right next to a variable, it means multiplication. So, in this one, I can skip step 1. I do not have addition or subtraction, so I do not need common denominators. What I am going to do, though, is go on to step 2, which tells me to use the inverse operation. So if I had multiplication, I'm going to divide by 3/4 and divide here by 3/4. These will then cancel out, so I'll be left with x equals, what I have to remember here though is that 9 over 20 divided by 3/4 means I need to multiply by the reciprocal. I need to flip it. So I'm going to multiply by 4 over 3. Now I'm going to look for any numbers that I can cancel out. So I notice 3 and 9. If I divide 3 by 3, I get 1. If I divide 9 by 3, I get 3. 4 and 20 are also related. If I divide 4 by 4, I get 1. 20 divided by 4 is 5. And that tells me that my answer is x equals 3/5. Now again, I can go back and check my answer. If I do 3/4 in my original problem, right here, and instead I put x there, when I rewrite I'm going to put times 3 over 5. If I do that, I multiply across the top, get 3 times 3 is 9, 4 times 5 is 20, and since 9 over 20th matches 9 over 20th, I know that 3/5 is correct. The other thing I can take a look at with multiplication is that, again, I can still check my answer, but I need to remember I did not need those equivalent fractions. In the last example that we're going to do together, I immediately notice that the operation I have is division. So that tells me I can skip step 1 and move directly on to step 2, in which case I'm going to use my inverse operation. Since I had division, this time I'm going to be multiplying by 2/3, and I'm going to do that to both sides. So those will cancel out. I'll be left with my x isolated on the left. On this side, I'm going to look for parts that I can cancel. Well, 3 and 9, I again notice I can divide 3 into 3 and get 1, 3 into 9 and get 3. I can divide 2 into 2 and get 1, and 2 into 10 and get 5. And what I'm going to find then is I have 3/5 as my numerator, or as my answer. This is interesting to me because on the last slide I noticed that I also had 3/5 as an answer. So let's see how this works when I check my answer out. When I have x, or I substitute back into my original equation, instead of this x here, I'm going to write my answer of x equals 3/5. So I have 3/5 divided by, and then back from this question I had 2/3. So I'm going to put 2/3. Now to actually solve 3/5 divided by 2/3, I'm going to have to flip it. So I'm going to keep the original fraction, change the sign to multiply, use the reciprocal, which will just be 3/2, and if I multiply, I'm going to get 9/10 as my answer. So since 9/10 matches the 9/10 here, I know that 3/5 is the correct answer, and I can be confident with that. So now use the same procedure to answer the last couple questions on your note skeleton. Make sure that you show what you did to both sides and show all your work that you used to help isolate your variable.